In the last video, we looked at how to solve a problem where we had pollution leaving a lake that depends on seasonal rainfall, as compared to the video before where we had a constant rate. In this video, we're going to take a look at what happens when we vary that, abruptly starting and stopping the water flow, as would be done by an upstream dam, in 1 month intervals of on and off, and in 6 month intervals of on and off. So let's get into it. So how would we even solve something like that? Well, I have them graphed out here. Here's the 1 month intervals where the water begins and stops. So that would be that the dam releases water and that water is flowing at a specific and continuous rate until they stop it for 1 month and then start it again for 1 month and so on. In this other case, this red line here, this represents what would happen if they began flowing that water for 6 months at a time and then stopping it for 6 months, compared to continuously flowing water at the same rate all year, every month to month. So how did I derive this? Well, we need a function that abruptly starts and stops. So let's go ahead and try to figure that out. How would we do something like that? Well, we're using a cosine function. So what do we need to do? Well, we need to square this out, and there's a few ways we can do that. One is to do it like this, where we just divide the cosine divided by the absolute value of the cosine, and we get a function that jumps from one value down to another. So discontinuous. Another option would be to do something like this, where we take basically the same thing. A third option would be to do something like this. Each one has roughly the same behavior, but can be quite different when we approach it based on how the software handles each of these cases. Another way that we might do it is something like this. And this is my preferred method. Find a function like so, and then we just simply take the derivative of that function to give us a square wave. Remove these other ones for clarity. And we have basically what we want. Now we scale this function here. And the reason I like this is because when we integrate that, we already know what the integral of this function is going to be. So how do we scale that? Well, first we add at least 1. Then we see that we're up at 2. So we go ahead and multiply that by 1/2. But now horizontally, we see that we're not scaling for 1 month or 6 months. So we need to scale that. So of course we always multiply by pi to get it into increments of 1 at first, and then what do we do from here? Obviously that changed our scaling. So let's go ahead and then multiply this by 6 over pi, 1 over pi. And here we go. We're back to scaled correctly between 1 and 0, on for 1 month, off for 1 month, on for 1 month, off, and so on. And if we want to do the same thing for 6 months, we divide that by 6 and then multiply this by 6. You might be wondering, how do I know all that? How do I know what to enter here? Well, you'd be surprised what guess and check does for you, right? There's no special way other than just doing it and checking what you have. How can you make whatever function you're dealing with look the way you need it to look in order to use it? So let's go ahead and set up our differential equation. As before, what we're doing now is representing the flow rate as a function of time, where this is some value multiplied by our flow rate. So if our flow rate is R, then R multiplied by 100% is just the flow rate we get. And then it abruptly stops, so R multiplied by 0 now gives us 0. There's nothing flowing. But you probably don't have much experience working with this kind of function, because generally in calculus we like to avoid discontinuous functions. But that doesn't mean that they don't have use. So how do we get this? Well, let's go ahead and set up our differential equation in the same fashion as we did before. So what do we have? We end up getting something very similar as before. Again, we're modeling pollution leaving a lake. We're saying that it's in there thoroughly mixed and water enters and leaves at the same rate. In this case, we're saying an upstream dam is controlling the release of water, And we're going to model two different things. We're going to model it on a 6-month period where the dam is releasing water at the same rate for 6 months, and then it shuts the valve or whatever it shuts, and it stops releasing something. Then we're going to look at the case where it's 1 month, releases water for 1 month, and then stops, and then releases, and then stops. As we know, there's pollution in that lake, and we're just modeling when we can expect it to leave. So let's set up our differential equation. We get dP, the change in pollution, divided by dt, the change in time. And that's going to be equal to negative r of t, a function of time that represents our rate, multiplied by p divided by v. In order to add a splash of excitement, I've composed another song so that you could enjoy that while you watch this math animation. And then we'll get back to the graph. Okay, wasn't that thrilling? So let's take a look at how this all stacks up. Again, let's assign some parameters to our equation. A, the initial value of pollutant, let's say that's 50 grams, 50 pounds, 50 whatever you need it to be. R is 0.7, let's say 0.7 thousand per month. V is 8, the volume of our lake, and we're saying that volume is constant, 8,000, let's say. First, we get our equation set up, and that's going to be equal to A, our initial value, multiplied by e to the negative r divided by v, 2v, multiplied by x plus 6 over pi, the 6-month equation, arc cosine of pi x over 6, and that gives us this equation up here. I just use the functional notation here, but here is exactly what we have. And of course, for the 1-month situation, just copy and paste. And all we do is change this 6 here to a 1 and change this 6 here to a 1 as well. And that gives us our equation. If we want to see what it's like to vary that, we could just put a as a variable here and divide by a. That changes the period length. And we could see from 1 month to however long we need. All right? Isn't that exciting? So say, it happens every 10 months where it releases at a maximum rate for 10 months and then it stops. And we see it kind of follows the sinusoidal one. Let's see, I have that up here. It's a safe bet to use this function here because it's differentiable and it's very convenient to use. We don't usually like having sharp corners. Okay, let's say we didn't know how to solve this. right? Let's say we didn't know what we were doing, right? Let's say we almost didn't know what we're doing. How would we solve that? Right? Say instead of differentiating the function that I gave you, this arc cosine stuff, instead of using that technique, what if we used one of the other functions? Let's say we used our cosine x divided by the absolute value of cosine x. And we, of course, scale that appropriately. Let's use sine x. How about that? There we go. Better. So we have 1 month on, 1 month off. That's the function we need. What if we don't know how to integrate that? Well, that's no biggie, right? Let's just say f of x is equal to that. And then we'll just go ahead and set up our integral as normal. I'll just skip to the solved part where we have 50, which is the initial concentration of our pollutant, multiplied by e to the negative 0.7, the rate, divided by the volume, which was 8, multiplied now by the integral from 0 to x of f of y dy. But remove that. Let's zoom out. It says it's graphed. And here we go. Now, as you can see, we didn't know how to solve this. Or in this case, we didn't even want to bother trying to figure that out. So we said, okay, we have a software here, and that software is capable of integrating. This is taking the indefinite integral of this function. As you might recall, when you take the indefinite integral, you get this function plus some constant. So this method includes that constant. For example, let's open a new window and let's define some more functions. Let's say we have a function f of x is equal to cosine of x. And we take the integral from 0 to x of cosine y dy, and we get, as we expect, the sine function. Okay, but now, what if we were to integrate from 0 to x sine of y dy? That's strange, isn't it? We have 1 plus a negative cosine function, but the integral of sine should be negative cosine. So this method provides us, let me remove these other things here. So this method provides us that constant we always talk about. We're taking the indefinite integral, but when we integrate, we have some unknown constant that depends on our starting point. So for example, if I was going to start at pi halves, then I just have what we expect, which is negative cosine of x. See, they align perfectly. That's why every time we do the integration, we always write that plus c, because that would be there no matter what. It just so happens whenever we choose this particular starting point wisely, it can be 0, and that's very convenient. But it doesn't have to be, right? No matter what we do, we're still taking an indefinite integral where we start at 2, or whether we start at any other value, 8 maybe. So whatever it is, let's start it. Let's actually vary that. And let's say a is equal to 1. Okay, now let's move it around. As we change that constant that we're starting the integration at, it goes up and down. So we could perform an indefinite integral without even knowing how. Right? We don't have to know what this is. We just have to know how to enter it into this system. And that gives us a little intuition about where that plus c always comes from whenever we integrate something. As you can see, the software is having quite a bit of difficulty here. But in general, we've done a great job. We have the model that we could compare to the standard model of having no fluctuations whatsoever in the rate parameter versus having the rate parameter depend on a function that's based on the rainfall, as we have here. And we could have it, as we see, it aligns quite nicely with the original function until we shut off the water. And then at that point, it generally follows the kind of characteristic function we'd see if we have rainfall increasing and decreasing through the year. Okay, so there we have it. Thanks for stopping by, and I'll see you next time. Don't forget to like and subscribe on your way out, and don't forget to go to mymerchoutlet.com where you can get tons of great stuff. Again, that's mymerchoutlet.com.